All right, hi there, everyone. As she said, my name's Ian Henriksen. I'm from Brigham Young University, and I'm going to be talking today about, as the title says, circumventing the linker using the Cython API for BLAS and LAPACK. So this is just connected to a bunch of work that I've done for SciPy recently, just in this past year, and I wanted to come and give a talk about it because I'm hoping that it'll be useful to a lot of people. So. First off, just a very fast introduction. BLAS and LAPACK, these are a bunch of high-performance linear algebra libraries. They have a Fortran interface, and so you have to deal with often some of the different naming conventions used internally by the different Fortran compilers in their object files. And then there are a whole bunch of different versions for these too. So you have, well, these are all the ones supported by NumPy, as to my knowledge, and usually you have to deal with selecting which version of the library that you're going to use and then finding the proper headers, linking against it, etc. And they're used extensively within the SciPy stack. So for example, whenever you do NumPy dot or a solve operation or any other sort of linear algebra thing, it goes down and dispatches to some of these high-performance Fortran routines, or sometimes they're also implemented in C or assembly, depending on which version you're using. So in this talk, I'd like to, first I'm going to show an example of the problem that I'm trying to solve. I'm going to discuss some of the problems that this particular example exhibits, and then I'm going to transition to demonstrating how this problem can be solved in general. So I'll let you know when I'm at each part. So first off, just a very naive Python algorithm. This is just a tri-diagonal solve. And it's done by just constructing a matrix of zeros, and then just filling in the diagonal elements and solving. And for simple problems, this works great, but it's a whole order of complexity harder than it has to be for the computer to actually compute this. And so you usually want to dispatch to something that's better, and you can actually use a routine that is in LAPACK to do this. So just DGTSV, and this will do it in order n rather than whatever it is that the solver that you're using beforehand does. So this is Cython. This is a little bit of Cython code, and here all I do is I just tell Cython, here is what this function that I'm going to be calling externally looks like. And there is, here's how I'm going to call it on an array that I've passed in. So it's pretty straightforward up till this point. The catch is now I have to write a setup script for this. And all of a sudden things get really hard because I have to deal with things like, finding the existing BLAS and LAPACK installations, finding all the right headers, actually dealing with, the different compiler name mingling schemes, choosing, if there are multiple versions installed, which one I want to use, and then also applying any known patches. So, for example, Accelerate recently had a bug where it would crash whenever the user would call the matrix vector multiplication for single precision floating point, if I remember right. And so you want to patch for things like that, or you can just hope that the code that you're writing or wrapping doesn't actually use that routine. But you actually want to patch for stuff like that. You usually want to link statically so that you can distribute the binaries. So that makes it so that every separate library that you're going to be distributing that does this has to have their own copy of the routines that they use internally. And then you also need to recompile whenever you do any changes in the library because everything's linked statically. And every module has to handle all of this separately. And so, unless you are already inside a module that has all of these problems sorted out for you, you have to deal with all of these problems every time that you make an extension module for Python that wants to use these functions. It's kind of a pain. Especially on, for example, Windows machines, where often the users that you're working with won't necessarily even have BLAS or LAPACK installed. anywhere. And so if you want to distribute in binary form, all of a sudden this gets a world harder because you have to do all of the static stuff to make it work. So currently we have things like this, where we have the library in the middle and everybody links to it statically and distributes their binaries from there. And they have to deal with all of the overhead of, finding it, patching it, determining which version they want to use, dealing with the different naming schemes used by different Fortran compilers, etc. And NumPy actually exports a little bit of this functionality. They have some stuff that'll actually help you find the LAPACK installation that was used to compile NumPy, but a lot of the other issues are still not really usable outside of NumPy and SciPy. So it would be nice if we could actually get this to something that looks a little more like this, where we have one module exporting interface for the library, and then other Python modules can just use the version in that library without having to mess with all of this finding and linking and patching stuff. And that is where Cython comes in to help. So the fundamental idea here of what I've done is that Cython already has a way to share C-level Cython declared functions between Cython modules. And you can do this via a PXD file that includes the header and links against the original library, but you can also do this by just making a Cython shim around the LAPACK function that you're wanting to wrap, and then just exporting that directly between the modules without having to include any headers or link against any libraries. The linking is done dynamically through Python. If I understand correctly, they pass a function pointer through the modules via Python capsule object. And so rather than having to link against the original modules, you get a function pointer to the function that you want to use. And all of this hassle with having to find and use the correct library suddenly goes away. And so you can export this, so direct linking is no longer needed. And then a single module exports all the needed routines. So somebody still has to go through all of this trouble of actually exporting this API. But the thing is that SciPy already has solutions for many of these linking problems. F2Py has gone through an enormous amount of work many years past to make sure that you can actually use a variety of different Fortran compilers. And SciPy, because they're used so heavily and they have so many different Fortran libraries that they maintain internally, or that they have to have this working already. And so because they've already solved this problem, it was basically just a matter of including the Cython shims as a part of their library, and then just going from there. And then other modules now just get to load them dynamically if they want to. So yeah, and then also one of the other perks is that if there are any upgrades or changes in the BLAS or LAPACK library that you want to use, since you're loading them dynamically, that's dealt with when you import SciPy and use the Cython version. So here's the example revisited. This is actually even easier in Cython now than it was before. So you can see I have pretty much the same file. But rather than having to tell Cython how to deal with this function that I want to include, I just go and say, import it from here. The declaration's there. And it imports it. I can use it the exact same way as before. We're following Fortran's calling convention where you pass everything via pointers. So that's something to keep in mind when you're using this. And yeah, so that's it. So now, because I really believe in this approach and really would like to see this in a lot of other libraries, I'm going to very quickly talk you through how you could do this for a C function and then a Fortran function. It's actually a very, very simple process, and it's something that I'm working on extending to other libraries right now. And so, yeah. So here's just an example C function with a corresponding header that you might want to wrap. It's very simple. I did it pretty much bare minimum for the presentation. So I'm just going to say, I want to call this from Cython modules without having to link against anything. And so what I'm going to do is I will, in my Cython module that's exporting this function, I will declare it as coming from this header. I'll make sure that I have the distutils stuff set up to actually include the proper libraries here. Since I only compiled this to an object, since it's a small thing, I used the extra link args there instead of the libraries for distutils, but you can use either one when you're dealing with a library, if I understand correctly. And then you just define a Cython shim that redirects your arguments. It's pretty straightforward. And then you, in your PXD file, you do not include the header, nor any of the extra linking stuff that you need to do for this. You just include the Cython function declaration. And then there's a setup file. It's basically just a generic Cython setup, with the exception that in this previous slide I used a directive to tell it to link against the object file that I've created. So there's that. And other modules now can use this function. Once this is compiled and installed, they can use this without having to link at all. And that's really nice. So the slightly longer example, this is a bit harder. This is exporting a Fortran function. And this shows what I'm going to do here is I'm going to use Cython in conjunction with NumPy distutils. I'm going to use NumPy's distutils package to handle the different name mingling schemes and actually, not actually have to call the compiler myself. I'm going to have it compile the library for me. And then I'm going to, again, just export an API via Cython shim. So here are two examples. The first one is a Fortran function actually returning a value. In writing this, one of the things that we found really actually quite hard to get it to work in a platform-independent manner was wrapping the existing functions in BLAS and LAPACK, because something strange was going on with the compilers, and it was seg faulting in random times. And so the approach that we settled on was to wrap every function in a subroutine that modifies one of its arguments. So this is an example. Up top I have the function, and then on the bottom I have the subroutine that just calls the function and modifies one of its arguments. So there's the subroutine wrapper. Then from here I can include this header file. This is basically just copy-pasted out of a couple different places in SciPy where it's used. This is what they use to get the name mingling scheme right when they're calling the BLAS and LAPACK functions inside their C code. And all of these if-def statements come from this is actually copied from an F2Py header. And they, if I understand correctly, are defined by NumPy distutils as needed to deal with the different name mingling conventions. So whether you need 1 underscore at the beginning of your function, 2 underscores, whether it's all lowercase or all caps, since Fortran's case insensitive, they have different ways of storing it. This handles that. And then on top of that, here's just the header. This is another one that I included for platform independence. On some platforms, you can just do an extern declaration from here, but this ended up being necessary as well to get the linking to work out right on Windows. And then here in your Cython wrapper, you go ahead and just declare it coming from the header. With the shim, you use the name macro in the CNAME for the Cython declaration there, where you're telling it how to deal with the function. The CNAME is basically just telling Cython, in the Cython code, name it this, in the C code, name it that. It's a bit of a lower level thing in Cython that it's better to avoid using, but this is a case where it's very much justified. Then you'll notice as well that I've declared both functions as no-gills, so that when you call them, there's no Python interfacing, handling of the GIL, or anything like that involved. So yeah, and then you just declare the Cython shim. And in this case, you actually catch the output and the value that you've declared and return it. It's pretty straightforward still. And then for a subroutine, actually, you could, let's see. Yeah, for a subroutine, you could just call the subroutine directly. And then here in the PXD, like I did before, you just state the Cython wrapper. You do not state any of the headers or the linking libraries or anything of that sort. Now, the setup file, this one's slightly longer. Basically, all you do is you tell NumPy distutils that you're going to be compiling these 2 Fortran modules, or I guess I just compiled them as a single library in this example. And then from there, you tell it that you have a C file that will create a Python C extension. And the C extension, the way you get the Cython to be called on the code, the way I did it here was just calling Cythonize on it, but not actually using the extension that it creates. So there you lose some of the inline comments for configuring distutils, but other than that, it works the same. You still get the same C file. NumPy distutils takes care of setting all the flags that you need, and there you have a module that exports a Fortran routine. So, couple closing thoughts. First off, many thanks to the SciPy developers. I originally released this as a external module, but we did some of the work to get it into SciPy, and they helped a great deal with a lot of this process. The code, this version of, I guess, wrapping it this way is something that's changed quite a bit from when I started working on this. And then, so a couple things that I'd like to see at some point, depending on, time permitting, I may implement these myself, are fused type wrappers, so you can do type dispatching within Cython. Also, wrapping more libraries, that's something I'm working on right now. And then also dynamically loading C++ classes. That's actually kind of a tricky problem that I haven't figured out, but I'd really love to see. So, thank you very much. Okay, any questions? Yeah, so it's so the question is most of this exposed through through SciPy.linalg? Yeah, the module is actually let's see, it's SciPy.linalg.Cython BLAS and Cython LAPACK. And those two modules export the exact routines are pretty much the ones that are in 3.1 through 3.5 versions of LAPACK that have been in all of those stable versions consistently without any change signatures. Is exactly what I import. I actually used F2Py. I used their kind of like a primitive parser that they use for Fortran to just generate the signatures on the fly and generate all of the code that's in there. And so they're very complete wrappers. The only exceptions are the ones that aren't consistent across the versions. So, other questions? Yeah.
Just a comment. This is awesome.
Thanks.
I watched the PR and I'm really glad we saw this here and got this into SciPy. That's super, super exciting.
Yeah, thank you. Yeah, so the comment is just that this is really great to be in SciPy, and I'm grateful. I'm hoping this is very useful to people. It's something that I just developed as a side project. So, other questions? All right, thank you very much.